Spring 24, question 1. Use method of induction to prove this. Step number 1, prove that P of 1 is true. How do we prove it's true? The first number in natural numbers is 1. So 2 times 1 equals to 1 squared plus 1. It's 2 equals to 2, which is true. Step 2, assume it's true for n equals to k. So it will be 2k equals to k squared plus k. Step number 3, prove it's true for n equals to k plus 1. To prove it's true, to this side I'll add a 2k plus 1. So whatever we add to this side, we have to add to the other side. It will be 2 times k plus 1. Okay. Now, for this side, it will be 2k plus 2. Taking common factor out, it will be k plus 1. Our k plus 1 is the n, so 2n. Okay, so this side is proved. Now, the other side. The other side is n, which is k plus 1, squared plus n, which is k plus 1. Okay, if I want to expand this, it will be k squared plus 2k plus 1 plus k plus 1. Okay, this is k cubed, no, I mean k squared plus 3k plus 2. Okay, now let me do it here. It's k squared plus k plus 2k plus 2, which is k squared plus 3k plus 2, which is the same thing I got here. Okay, so I can rewrite it as k plus 1 squared plus k plus 1. And k plus 1 is n. Okay, so it will be n squared plus n, and here 2n. So it's proved by induction. Okay, we need to prove this. So I have to, I'm gonna use an element method. If I choose like an element x that belongs to a minus b, this means x can be an element of b and x not an element of b, which means it's an element of the b complement, and it can be, or it can be, x does not belong to a and belongs to b, which means it belongs to a complement. So this x can belong to a complement or b complement. Question 3, we have to prove it's bijective. How do we prove it? First, if it's injective. So if f of x1, y1 is equals to f of x2, y2, then x1, y1 should be, then these should be equal to each other. Okay, so 2x1 plus sine x1 equals to 2x2 plus sine x2. Okay, so if I want to simplify, these will delete. Okay, but I can, first, these are periodic functions, they can never be injective, but to prove it, I can use a counterexample. For example, if we had two different inputs, for example, x1 is 0, x2 is pi, and I plug them, sine 0 is 0, sine pi is pi, 0. So two different inputs giving the same output is not injective. Okay, so I proved it by a counterexample. Next, is it surjective or not? Okay. So I want to check if the codomain of the function, which is all real numbers, is it equal to the range of the function? Okay, the function is 2x plus sine x. 2x, the range is all real numbers, okay? But sine x, the range of sine x is from -1 to 1, okay? So the range of the function is not equal to the codomain of the function. It's not all real numbers. Here it has a restriction from -1 to 1. Okay, so since they're not equal, it's not surjective. Okay, so since it's not injective, not surjective, it will be not bijective. Discuss if the statement represents a tautology or not. Tautology means it's always true, okay? Using truth tables will give you 50% of the mark. So what can we do? First, here I can simplify it. I can use the distributive method, P or not Q or Q. No, I mean not Q and Q, or P and R. Okay. So first, let's discuss this. If Q is true, not Q is false. If Q is false, not Q is true. Okay. وني بينهم and ف true and false is false. False and true is false. So this will always be false, okay? I'll continue here. So P and I'll replace this with false, okay? Or P and R. هنا. If P was true and R was false, it will be true and false, which is false. Okay, but if P was false and R was true, false and true is also false. Okay, now if P was false and R was false, false and false is false. If P was true and R was true, true and true is false. Okay, so this expression can be true or false. Okay, so let's try if it was false. False or false is false or false is false. So P and false. Okay, if it was false, P is either true or false. Okay, so if it was true or false is true, and if it was false, it's false. So it will not always be a tautology. It will not be a tautology. It will not always be true. It can be true, it can be false. So you can make a conclusion in it's not tautology. Okay, now part B. First I need to distribute this Q and not P, and not P or not R. Okay, now I can distribute. It will be Q and not R, or not P and not P. Okay, so first let's discuss this. If P was true, not P is false. Okay, so this expression will be true and false, which is false. If P was false, not P will be true. So again it will be false and true, which is false. Okay, so in all cases this will be false. Let's discuss this. Q can be true, Q can be false. R can be true, which means not R is false, and R can be false, which means not R can be true. I mean, it should be true. Here, true and false is false. And false and true is false. False or false is false. So it will always be false. So I can make a conclusion. It's not a tautology. Let P, Q, and R be statements. Use logical equivalences to prove this. Okay. First, I'll do this. Let's assume this is P and this is Q. P implies Q can be not P. Wait. P implies Q, not P or Q. Okay, so not P or Q. This will be not P or not Q or R. I can, it's like this, but I can rearrange it. It can be not P and not Q or R. Anyway, I did this. Okay. This can be Q implies R, because this is not P or Q. Okay. Then not P or this. Let's assume this is Q, this is P. This can be P implies Q, which is true. Part B. P implies Q or S implies R. Okay. I can use this. P implies Q is equivalent to not Q implies P. So this will be not S2 R imply لا wait. أول شيء P P implies Q is equivalent to not P or Q, okay? So this can be not P or Q, or this can be not S or R, okay? الحين I can use distributive property. It will be not P or not S or Q or R, اوكي، لانهم يبونهم شيء عدل بعد. بعدين let's imagine، لا wait، اروم اطلع النوت برا، تكون P and S and هذا. الحين we can imagine ان هذه not P or Q عشان نحولها نفس شي، فبتكون P اللي هي P and S implies Q اللي هي Q and R، okay. الحين I can use ان ال P implies Q is equivalent to not Q implies P implies not P، هذا by contrapositive، okay. So it will be not Q and R implies not P and S. So this will get distributed. It will be not Q or not R implies not P or not S, which is true. Prove or disprove if a relation is symmetric and transitive, then it's reflexive. Okay. If like I have a set 1, 2 and 3, symmetric means let's call them A, B, C. Oh no, then X, Y and Z, okay. Symmetric means X is related to Y, Y related to X. Transitive means X to Y, Y to Z, then X to Z. Reflexive is just X and X. Okay. If I write this, it will be, because we know that the relation is symmetric and transitive, okay? So for symmetric, 1 related to 2, 2 related to 1. Transitive, 1 related to 2, 2 related to 3, 1 related to 3, okay? So if my relation was this, from these there is no relation that is reflexive. There is no 1 and 1, 2 and 2, or 3 and 3. So it's not reflexive. But this is disproving by a counterexample. Prove or disprove that for any positive real number x, for any x that is a real number, positive, the difference between x and x to the power of negative 1, x minus x to the power of negative 1, is greater than or equal to 2. Okay? This is the same as saying x minus 1 over x greater than or equal to 2. Before choosing to prove or disprove, we can check using numbers. If I plug x equals to 1, it will be 0. 0 is not greater than or equal to 2. So this means we are disproving. Okay? X minus 1 over x. I can make a common factor. So it will be x squared minus 1 over x greater than or equal to 2. X squared minus 1 over x minus 2 greater than or equal to 0. And then this is my counter example. Plugging 1 will give me a wrong answer.